Hi, this is lesson 3 for unit 4 in our chemistry class, and in this lesson we'll be talking about the Kelvin scale as well as how to solve for Charles' law problems. For our lesson objective says students will learn how to convert Celsius to the Kelvin scale. Students will also be able to use the Kelvin scale in Charles' law to understand the relationship between volume and temperature.
Let's go ahead and get started with the Kelvin scale. William Thomson, known as Lord Kelvin, developed the absolute temperature scale known as the Kelvin scale. 0 on the Kelvin scale is the lowest temperature possible. This is known as absolute 0. And at that temperature, there is no molecular motion. Molecules no longer move. That is known as the coldest temperature possible. Now let's take a moment to discuss how Lord Kelvin came about with figuring out what absolute 0 was. On this graph you see right here, we have 3 different gases, A, B, and C. Now, as you cool down a gas, the molecules begin to move slower. So therefore, they exert less pressure on the walls of its container, and therefore, the container becomes smaller, so the volume decreases. So as you decrease the temperature, the volume becomes smaller and smaller and smaller and smaller. If you go ahead and you graph it, you'll get a line that looks a lot like what you see in this graph. Now, that is true for gas A, you see right there, but it's also true for B and C. We have 3 different gases in this graph, and all of them, as you cool them down, the volumes become smaller and smaller and smaller. That's because the molecules, again, are going slower and slower and slower. And if you keep on dropping the temperature further and further and further, what happens, the molecules will keep on slowing and slowing and slowing, exerting less pressure. The volume becomes smaller and smaller and smaller. At some point, if you slow down enough, those molecules will come to a full stop. That means that they cannot go any slower. The molecules have reached a full stop, the volume becomes 0. And on the graph, all gases, doesn't matter what they were, A, B, or C in this example, they all reach the same volume of 0 at a temperature of negative 273.15 degrees Celsius. That was what Lord Kelvin theorized to be the lowest temperature possible. Because after all, you slow down those molecules to the point where they stop. Can the molecules really go any slower than full stop? Like, no, that is as slow as they can go. So therefore, that is the lowest temperature possible. So he called that absolute 0, and that is the beginning of the Kelvin scale. So absolute 0 is 0 Kelvin. And since Celsius and Kelvins have the same magnitude in each degree, then they're very much related to each other by that equation you see here on the slide. So how do you change from Celsius to Kelvin? You would add 273 plus the temperature in Celsius to change that to Kelvin. Now that we have that formula, let's go ahead and put it to use in some examples.
In example number 1, we're asked to do the following conversions. They're given to us temperatures in Celsius, and they say, can you go ahead and change them all to the Kelvin scale? The formula for changing from Celsius to Kelvin is very simple. This is a formula where you get your temperature in Celsius and you add 273 to your given temperature, and that will give you your answer in Kelvin. So let's go ahead and do that. The first one, let's see, they give us 20 degrees Celsius, change it to Kelvin. So all I got to do is add 273. So that'll give me 293 Kelvin. Let's call that one A. That'll be the first one. For letter B, they go ahead and they give us 27 degrees Celsius. And we're going to add 273 to it, so that gives us 300 Kelvin. So that'll be the answer for letter B. Letter C, we're given 150 degrees Celsius. And again, can you convert it to Kelvin? So we're going to go ahead and do that. Again, you just add 273. And so we're going to go ahead and get the following. Let's see, 7 plus 5 is going to give us 2, goes 1, 423 Kelvin. And lastly, letter D, which is the last one right here, we get negative 20 degrees Celsius. Change that to Kelvin, so it'll be negative 20 degrees Celsius plus 273. So it's going to go ahead and give us 253 Kelvin. And those are the answers for example 1. In example 2, we're given temperatures in Kelvin and asked, can you take them from Kelvin back to Celsius? So this is the formula to go from Celsius to Kelvin. So if to go from Celsius to Kelvin, you would add 273. Now to go backwards, what would you have to do? Well, you would subtract 273. So what you would do is move the 273 over. So it would be whatever temperature you have in Kelvin minus 273. And that's going to give you your temperature in Celsius. All right, so that's what we're going to go ahead and do. So for our first one, let's call it A. We have 300 Kelvin. Can you switch it back to Celsius? Easy, we just go ahead and subtract 273 to it. So that's going to go ahead and give us 27 degrees Celsius. For letter B, we have 274 Kelvin. And again, they ask, can you switch it back to Celsius? Going backwards, negative 273, so it'll just give us 1 degree Celsius. For letter C, the third one, we're given 200 Kelvin. Switch it back to Celsius, so subtract 273, so it's going to give us negative 73 Celsius. And finally, letter D, we're given 500 Kelvin. And switch it back to Celsius, so you would subtract 273 from it. That's going to give us 227 degrees Celsius. And that's how you go back from Kelvin to Celsius. That takes care of example number 2.
Up next for us is Charles' law. Charles' law can be used to study the relationship between volume of a gas and temperature. The law states that at a constant pressure, the volume of gas varies directly with the temperature of that gas. So what that means is that as the temperature increases, the volume of the gas also increases. And vice versa, as the temperature of the gas decreases, the volume of the gas also decreases. The reason for that is because the molecules inside the gas are going to go ahead and speed up when you heat them up. So when they collide against the walls of its container, they're able to provide more force, and that stretches out the walls of its container. But if you cool down the gas inside of the container, they're going to move slower. When they collide against the walls of its container, they're going to have less force, and that will allow the container to go ahead and shrink. The formula for Charles' law is right there on the slide, where it's V1 over T1 is equal to V2 over T2. In that formula, think of V1 and T1 as the before, and V2 and T2 as the after. The V is for volume. And the volume could be measured in either liters, milliliters, centiliters, really any volume unit. The T, though, for temperature has to be measured in Kelvin. So we're using absolute temperature. And the formula for Kelvin is right there at the bottom of the slide. If you want to change the temperature in Celsius to Kelvin, you get that temperature in Celsius and simply add 273, and that will give you your answer in Kelvin. Now, a couple applications for Charles' law. For example, in a hot air balloon, the reason why it rises is because the balloon will expand and it will give it a lower density when compared to the cool air around it, and that will make it rise. Now, the second picture you see right there, that's a little button that pops up when you're cooking a turkey. How does that work? As the temperature increases, the gas inside of the little tube also increases. When it reaches the right temperature, that's enough pressure to push out the little button, and that's going to go ahead and indicate that the inside of the turkey is hot enough to be consumed. The third picture has a little ping pong ball. And if you ever had one, it gets a little bit dented. One of the things you could do is you go ahead and you heat it. So put the little ping pong ball into some warm water, and that's going to go ahead and get the molecules inside of the ball to move faster. They're going to go ahead and collide against the walls of its container, in this case the ball, with more force, and that will pop it back into its regular shape. Next, the last picture right there, you see a person running in the snow. And the cold temperature does affect the function of the lungs, and that is anticipated by Charles' law. So if you ever ran in really, really cold weather and you feel like you're not really having a great outing as far as working out, it is related to how the cold air affects your lungs.
In example 3, we're asked the following question. The gas has a volume of 24 liters at a temperature of 27 degrees Celsius. What volume will the gas have at 127 degrees Celsius? And for this problem, the pressure remains constant. That means we're not going to change it. We're only changing the temperature and the volume. So what happens to the volume of the gas? So first of all, look at the sentence structure. The first sentence up to the comma right here will give you the information you need for the before. The V1, T1 are your before. The V2, T2 are the after. So it says a gas has a volume of 24 liters at 27 degrees Celsius. So 24 liters at 27 degrees Celsius. Then they go ahead and they ask you, what volume, so I'm just going to put the symbol for it because we don't have it, what volume will the gas have at 127 degrees Celsius? So that will be your setup. The initial temperature was 27, the new temperature was 127. They want to know what happens to this gas. Will it become bigger? Yeah, we're increasing the temperature, so therefore the gas will increase. Now we're going to go ahead and solve for V2, but before we go any further, I wanted to point out the temperatures right here. You will notice that they are in Celsius, and we cannot use that. All temperatures for Boyle's law, Charles' law, combined gas law, all of them have to be in Kelvin. So actually a first step should have been getting those temperatures and changing them to Kelvin. So to do that, you get your temperature in Celsius and you add 273. So the first one's really 300 Kelvin, and the other one 127 plus 273, it goes 400 Kelvin. So let's go ahead and replace them with their actual values. So this will be 300 Kelvin, 400 Kelvin. Now we can go ahead and solve this problem. Easiest way to do this is just a little cross multiplication. So we're going to go ahead and multiply V2 times 300 Kelvin. So it'll be 300 times V2. And on the other side, we're going to go ahead and get 24 multiplied times 400. 24 times 400 gives me 9600. Now I want V2 isolated, so I want to get rid of the 300. So I'm going to divide by 300. And there we go. So it's going to go as V2 equals 9600 divided by 300. 32 liters. I know it's in liters because the volume was initially in liters. So it remains in the same unit. So there's our answer for example number 3, 32 liters. It expanded from 24 to 32. In example number 4, we're asked the gas has a volume of 30 milliliters at a temperature of 77 degrees Celsius. At what temperature will the gas have a volume of 120 milliliters? So now we're looking for the temperature. So let's go ahead and substitute the values in, but don't forget that the temperature needs to be in Kelvin. So let's begin with that. We're given a temperature of 77 degrees Celsius, but I need that in Kelvin, so I'm going to add a plus 273, so it's going to go ahead and give me 350 Kelvin. So initial volume was 30 milliliters, V1 over a temperature of 77, but in Kelvin that is 350 Kelvin. And then they said, what temperature is needed to get a volume of 120? So our new volume we are looking for is 120. What temperature do we need for that to make that happen? Alright, so this part we're just going to go ahead and cross multiply. So I'm going to multiply 120 times 350. That's going to go ahead and give us an answer of 42,000. And it's going to be 30 times T2. It's just 30 times T2. I want to isolate the T2. That's my temperature. So I'm going to divide both sides by 30. So it's going to be 42,000 divided by 30. That gives us 1,400 Kelvin. That will be the temperature you need to raise from 350 Kelvin to 1,400 Kelvin so that you can expand the volume from 30 milliliters to 120 milliliters. That takes care of example 4. In example 5, we're asked, the gas has a volume of 50 milliliters at a temperature of 227 degrees Celsius. What volume will the gas have at 127 degrees Celsius? So now we're going to go ahead and cool down from 227 down to 127, and they want to know what's going to happen to the volume. Well, we know that the volume will reduce, but what will it really be? First of all, before we continue, notice that the temperatures are in Celsius, so we need to change those to Kelvin. So it's going to be V1 T1 equals V2 over T2. That's our formula for Charles' law. And changing those temperatures, 227 degrees Celsius plus 273, that's going to go ahead and give us 500 Kelvin. And the second temperature was 127 degrees Celsius plus 273, that gives us 400 Kelvin. So those are the temperatures that we're going to go ahead and plug in T1 and T2 in Kelvin, never in Celsius, always in Kelvin. So let's go ahead and plug all the numbers in. So we have a volume of 50 liters over a temperature of 227, who's really 500 Kelvin. And they want to know what volume, so V2, I'm going to put the symbol for V2, will it have at a temperature of 127 Celsius, which is really 400 Kelvin. Again, from here, what we do is we begin to cross multiply. So it's going to be V2 multiplied times 500. That just gives 500 times V2. And here it's going to be 50 times 400. That gives us 20,000. Finally, I want to isolate the V2, so I want to get rid of the 500. So I divide both sides by 500, so I can isolate the V2. So that's going to be 20,000 divided by 500. It'll give me 400, and it's going to be in liters because V1 was in liters, so therefore V2 will be in the same unit. And that takes care of example number 5. In example 6, we're asked a gas has a volume of 900 centimeters cubed and a temperature of 100 Kelvin. What temperature will the gas have at 450 centimeters cubed? So if we reduce the volume from 900 to 450, what temperature is that? I want to point out a couple of things about this problem. Number one is that the temperature is already in Kelvin, so we don't have to change it to Kelvin. It's already given to us in Kelvin. And centimeter cube, that's another unit for volume. So the first sentence, it tells us here's your volume, there's your temperature, so we substitute them in. So you have 900 centimeters cubed over a temperature of 100 Kelvin. Now the second question, the second part, you ask what temperature will the gas have at 450 centimeters cubed. So 450 centimeters cubed, we want to know what will be this temperature, T2. Alright, so that's our setup. We're going to go ahead and cross multiply and solve this problem. So it's going to be 450 times 100. That'll give us 45,000. And 900 times T2 is just 900 T2. Next, I want to isolate the T2, so I want to get rid of the 900. So I'm going to divide by 900 on both sides. And that's going to go ahead and give me my answer. So it is 45,000 divided by 900 gives us an answer of 50 Kelvin. So that will be the answer. So notice that the temperature was originally at 100, and we dropped it down by half, so therefore that the volume at 900 will drop to 450, which is also half. So to drop half the volume, you need to drop half the temperature. Alright, that takes care of example number 6. This brings us to the end of lesson 3 for unit 4. Thank you so much for watching.